Across the silent plains of interstellar night where starlight drifts like cold dust and time stretches until it forgets itself, an object emerged small against the darkness yet ancient in its composure. Long before human eyes ever found it, before telescopes began their meticulous recording of its path. 3I Atlas had been wandering through a void where even memory fades. Out there, beyond the borders of our star's influence, it passed through regions where radiation washes all things clean of origin, and where the faintest fragment becomes a messenger from an age predating the sun. Its first whisper was not in the language of comets or asteroids, but in the subtle geometry of its arrival. It crossed the heliosphere not with the chaotic tumble expected of a frozen relic, but with the quiet precision of something that had travelled far and had not been broken by the journey. In those first moments of detection, when it was still a dim smear against the sensor arrays, a smaller truth pulsed beneath the scientific announcements. This visitor was the third interstellar object ever observed, yet already it stood apart from the two that came before it, as though it carried an intentionality embedded in the arithmetic of its trajectory. For centuries, humanity had imagined the skies as a stage for myths, then as a map for celestial mechanics, and eventually as a frontier for exploration. But now and then, the universe sends something that challenges the foundation beneath all three. 3I Atlas arrived, as one of those disturbances, a reminder that the cosmos still holds shadows deeper than our theories and perhaps histories, more complex than our instruments can yet decipher. When early observers studied its faint outline, the light scattering from its surface did not behave as the light from a simple comet should. Instead, it created a luminous envelope, a kind of uncertain halo that refused to give up the shape hidden within. In that vagueness was a quiet tension, a sense that what was approaching Earth was not merely another frozen wanderer escaping the pull of its birth star. The darkness beyond our system is wide, and countless objects drift through it. Yet this one seemed unusually deliberate, almost poised. As its designation was formalized 3, the third interstellar object to enter the solar system, its unofficial name began to wander through scientific circles and media broadcasts alike the alien object. Not because evidence supported that label, but because its behavior refused to sit comfortably within the categories created for familiar things. The term became an echo of our own uncertainties, a projection of a species that still looks up at night and wonders whether the void watches back. NASA prepared its first public release cautiously. The institution had learned from the global fascination triggered by Oumuamua, whose accelerated departure and cigar-like silhouette created debates still unresolved to this day. But with 3I Atlas, the stakes felt subtly higher. Its mass appeared too large. Its trajectory was too aligned. Its tail behaved in ways that seemed almost theatrical, disappearing and returning like signals rather than simple outgassing. To call it a comet was safe. To call it anything else was to open a door science often prefers to keep measured and controlled. Yet the poetic truth, the one that thrums beneath the data and the press releases, is that the cosmos rarely speaks in straight lines or tame behaviours. Sometimes it sends a riddle carved in ice and dust. Sometimes it sends an object from far away that forces us to slow our interpretations, to sit with the weight of possibility. And sometimes, as with 3I Atlas, it sends a traveller that appears ordinary only at first glance before revealing the faint seams where knowledge begins to fray. In the earliest images, fuzzy, unresolved, filtered through the algorithms that attempt to sharpen a whisper into a shape, 3I Atlas hovered like a question suspended in deep space. Scientists described it in technical terms, but the undertone of their analyses held a quiet respect. An interstellar object is not merely a rock, it is a piece of another solar system, a fragment of a world we will never see carrying within it the story of formation, rupture and escape. To encounter such a thing is to touch a relic of cosmic history, older than any human civilization, older even than Earth's own continents. And yet this fragment did not behave like fragments should. Its mass, its reflectivity, its rotation, its tail, each element presented an edge that did not quite fit, as if the object were composed of mismatched memories from multiple categories of celestial bodies. In the poetic silence of observation, one lingering question began to surface. What if this object was never meant to be merely understood, but to be witnessed? As it approached, whispering its ancient momentum into the inner system, telescopes turned toward it, with the reverence reserved for rare visitors. Not because it was threatening, but because it carried with it the weight of all that remains unknown. The dust trails of comets are usually signs of fragility, of sublimation, under the heat of the sun. But the behaviour of this object's tail-absent reversed reappearing created a pattern that resembled not decay but design. In this opening act, the narrative of 3Y Atlas is not yet about conclusions. It is about emergence, a slow unfurling from darkness into the realm of human perception. It is about an interstellar wanderer crossing the threshold of our sun's domain, carrying anomalies like quiet riddles, asking us not for belief but for attention. And in that attention, a deeper mystery begins to take shape. What kind of story does the universe tell when it sends something that behaves almost but not quite like the objects we know? It began as so many astronomical discoveries do, not with a grand declaration but with a flicker, an anomaly in a stream of data quietly flowing through observatories scattered across Earth's night side. Instruments were trained on regions of the sky mapped 1,000 times before searching for the familiar choreography of near-Earth objects, icy wanderers, and the faint signatures of distant asteroids. Yet, within those routine sweeps, a subtle motion betrayed the presence of something unexpected. A faint point of light shifting against the background stars with a velocity no solar-bound object should possess. The first astronomers who tracked it understood immediately that its path was unnatural in the most precise scientific sense. Its velocity exceeded the escape threshold of the sun, meaning it was not a child of our system. It was a visitor, a traveller from beyond the gravitational borders that hold the planets in their ancient circuits. The designation followed swiftly through to the third interstellar object ever identified. The atlas that accompanied its name came from the survey that detected it, a testament to the relentless gaze of automated sky watchers, built to notice the nearly imperceptible. But behind the formal announcement lay a deeper tremor. Ever since the discovery of 1I/Oumuamua several years earlier, astronomers had lived with a quiet expectation that the next interstellar visitor would help clarify the anomalies left by the first. That it would confirm whether Oumuamua's unnerving acceleration, its thinness, its light-sailing tendencies were unique or part of a broader class of interstellar debris. The hope was for clarity, a familiar-looking comet or asteroid drifting across the solar system on a hyperbolic arc. What they found instead was something that refused to echo the behaviour of its predecessors. Observatories around the world quickly trained their lenses upon it. Ground-based telescopes in Chile, Hawaii, Arizona and Spain captured its initial glimmer. Soon the orbit-classifying teams computed its inbound path with growing astonishment. Its trajectory was not inclined at some steep random angle relative to the solar system's plane, as one would expect from an object ejected violently from its native star. Instead, it approached with a strange and improbable alignment, drifting almost flush with the ecliptic, the same thin sheet upon which the planets revolve. This was not unheard of, but it was wildly unlikely, like finding a grain of sand falling perfectly along the seam of an ancient mosaic. Astronomers noted the coincidence, then noted it again. Was it simply a statistical rarity, or did it hint at something else? Perhaps not a design, but a history shaped by forces unlike those that governed comets born in the outskirts of our system. As the discovery rippled outward, the first scientific briefings offered early estimates of its brightness, its shape, and its likely composition. It appeared faint yet larger than expected, diffuse yet somehow stable in luminosity. The earliest observations suggested an object that refused to settle into the typical photometric patterns of a tumbling comet nucleus. Scientists debated whether it was simply shrouded in dust or wrapped in some form of gas that smoothed its profile to a luminous sphere. NASA prepared a preliminary set of images to share with the public, images that, despite considerable anticipation, showed little more than a fuzzy ball of light. This vagueness frustrated some observers, but for astronomers it was simply the beginning. Many understood that the earliest window of detection always deals in uncertainty, faint signatures, elongated streaks, and unresolved halos. Yet woven into those early imperfect visuals was a tension that would only deepen as stronger instruments turned their attention toward 3I Atlas. In academic circles, the discovery triggered a renewed debate about the frequency of interstellar objects. Prior to 2017, the scientific community had no confirmed examples. Then within only a few years came Oumuamua, followed by 2I/Borisov, now this much larger and much stranger visitor. If interstellar space truly contained so few free-floating remnants, why did the third one appear to be orders of magnitude more massive than the first two combined? And why had no object like it been seen before? This question began to circulate quietly through research groups, hinting that 3I Atlas might already be rewriting the statistical models of cosmic debris. The group at Harvard, led by Avi Loeb, was among the earliest to draw attention to the increasing complexity of these interstellar arrivals. Loeb had already highlighted over a dozen anomalies associated with this new object, anomalies that would soon define the discussion surrounding it. Yet before the speculation and controversy grew, the atmosphere of discovery carried a kind of reverent excitement. It was a fragment of another world, another solar system drifting into ours. Perhaps it had been cast out by a gravitational disturbance in its native birthplace. Perhaps it was the relic of a shattered planet orbiting a star long dead. Whatever its origin, it was a traveller whose story began far before the earliest human civilizations, long before the Earth cooled enough to host oceans. As the world's observatories continued to fix their gaze upon it, the instrumentation evolved. Spectrographs opened their prisms. Light curves began their quiet climb toward coherence. Data streamed into laboratories where algorithms passed motion, brightness, and shape with the emotionless rigor of computation. And through all of it, a sense of strangeness grew. The discovery phase was no longer merely about cataloguing what was seen. It was becoming an exercise in grappling with what resisted being seen, what remained hidden, elusive and inconsistent with the behavior of a natural comet. Each new measurement brought the object further into focus, yet somehow made the picture more ambiguous. 3i Atlas had entered the solar system, but it had also entered a tension between what is known and what is expected, between the comfort of classification and the friction of anomaly. The discovery was complete, yet comprehension had barely begun. And in the wake of its detection, a deeper disquiet began to trace the edges of scientific curiosity, a reminder that the universe is not obligated to behave according to our predictions nor to reveal its purpose swiftly. In the story of 3i Atlas discovery was only the first key turning in a door that had been closed for eons. From the moment astronomers began computing its physical characteristics, the first true shock of 3i Atlas emerged not from its erratic tail nor its improbable trajectory, but from something far more fundamental, its mass. In the discipline of interstellar object studies, a field still young, still raw, from the disruptive arrival of Oumuamua mass is not a trivial detail. It is the anchor of all interpretation. It defines the object's structure, its origin, its behavior under solar heating and the forces that act upon it. And in the case of this visitor, that anchor refused to obey the expectations carved into decades of astrophysical theory. Through its brightness and the inferred diameter that followed, scientists produced an estimate so far outside the norms that it immediately destabilized conventional explanations. The object appeared to be 1,000,000 times more massive than Oumuamua and 1,000 times more massive than Borisov, the two previous interstellar wanderers. This discrepancy was not subtle. It was vast, like discovering that the third grain of sand found on a beach weighed as much as a mountain. The cosmos is expansive beyond understanding, but it is not random in its distributions. The amount of material drifting freely between stars is limited. Stars do not casually eject enormous bodies into the void. Planetary systems form with their own gravitational syndromes, their debris fields, their histories of collisions and expulsions, but all within bounds. For an interstellar object of such mass to appear before Earth's telescopes was not merely unusual, it was discordant with the principles that govern planetary formation and stellar neighbourhood dynamics. Astrophysicists began rechecking their numbers, revisiting the algorithms that translated luminosity into size, attempting to discover some overlooked variable that could shrink the object down into a more comfortable category. But the data resisted such adjustments. The diffuse outline produced by telescopic imaging suggested a large clouded structure, something with significant surface area. And surface area implied volume, volume implied mass, the numbers held. To ground the anomaly, scientists compared 3i Atlas with what they knew of interstellar travellers. Oumuamua, elongated and thin, was so light that solar radiation pressure alone appeared to alter its course. Borisov, on the other hand, behaved more like a conventional comet, shedding gas and dust in a predictable arc as it approached the Sun. Between the two objects lay a spectrum of possible interstellar bodies. Yet 3i Atlas did not comfortably inhabit any region of that spectrum. It leapt beyond it, landing in a category that had no name. The question began to circulate in scientific discussions. How could such a massive body exist, remain intact, drift freely among the stars, and yet never have been detected before? The likelihood of encountering such an object was infinitesimally small. Based on existing models, if pieces of this scale roamed interstellar space with any frequency, Earth's telescopes should have already witnessed dozens, if not hundreds of them. Instead, this one arrived alone, silent, singular, and inexplicably large. Avi Loeb, known for his willingness to explore boundaries between natural astrophysics and technological possibilities, articulated the tension succinctly. If 3I Cratlas was truly this massive, then our understanding of the population of interstellar debris must be deeply flawed. Either the universe contains far more colossal wanderers than previously estimated, or this specific object is not representative of the natural distribution. The implications of either conclusion were immense. The scientific shock did not stop with mass alone. The relationship between size and behavior produced additional contradictions. A body so large should exhibit certain gravitational and rotational effects. Its surface should behave predictably, under solar heating generating outgassing consistent with known cometary physics. Its jets, if present, should smear and twist as the body rotated, reflecting the influence of centrifugal motion. But none of these effects were observed in the early data. A massive object with stable jets that defied rotational smearing was already puzzling. A massive object whose tail vanished and reappeared in inconsistent configurations was more puzzling still. Yet each of these mysteries was overshadowed by the largest question of all. How could something of this scale be drifting through the solar system now, when nothing like it had ever been seen before? The anomaly struck at the heart of the fledgling field studying interstellar visitors. Oumuamua had already disrupted expectations by behaving like neither asteroid nor comet. Borisov had then reassured the scientific community that natural interstellar comets did exist. But 3's atlas shattered that balance once more. Where Oumuamua had been small and evasive, this object was immense and opaque. Where Borisov had been predictable, this one was erratic. If scientists sought a pattern, they found instead a spreading map of contradictions. Mass and frequency are deeply tied. To have an object so massive appear as the third detected interstellar body implied one of two unsettling possibilities. Either our solar system is being visited by unusually massive objects at a rate far exceeding probability, or the first two objects were outliers, and this one represented a more normal scale. A normal that would require rewriting entire models of interstellar matter. Neither explanation fit comfortably within established physics. The broader scientific community reacted with caution. Some argued that early size estimates would shrink once more data arrived. Others proposed that the apparent mass was an illusion created by dust gas or extended coma activity, exaggerating its brightness. But even these conservative hypotheses struggled to reconcile the consistency of its luminosity with the irregularity of its outgassing. The numbers did not collapse as expected. Instead, they held their shape like a stubborn truth refusing to be simplified. There is a quiet moment in every scientific confrontation with the unknown, when the mind recognizes that the numbers have stopped aligning with the framework they were built to support. With 3 Iphicrates, that moment emerged early and unmistakably. The object's mass stood as a pillar of defiance, a signal that something about this visitor was dramatically different from what had been anticipated. And for those who study cosmic wanderers, the shock was not rooted in sensationalism nor in speculation about artificial origins, but in the simple pressing reality that the universe had introduced something that did not fit. Mass, the most basic of physical properties, had become the first rupture in the narrative, a crack from which deeper mysteries would soon widen. The motion of 3 Atlas across the sky should have been chaotic, or at least indifferent, arriving from some arbitrary tilted angle as most interstellar visitors do. Objects flung from distant systems are ejected through processes wild in their violence, planetary collisions, gravitational slingshots, perturbations around massive stars, or the slow unbinding of ancient planetary debris. These expulsions impart random trajectories, and randomness leaves a specific fingerprint, steep inclinations, sharp angular offsets, paths that slice through the solar system at oblique, unpredictable angles. Yet the orbit of 3 Atlas contained none of this disorder. As astronomers refined its inbound path with increasingly precise observations, a quiet astonishment began to form. The object was travelling almost exactly along the plane of the solar system, the thin gravitational sheet where the planets reside, where most major bodies in local space trace their long, slow revolutions. This alignment was not simply unusual in the statistical sense, it was deeply improbable. The solar system's ecliptic plane represents only a narrow slice of spatial orientation compared with the three-dimensional expanse of interstellar space. A random object from the galaxy should almost never arrive aligned with it. To picture the improbability, one might imagine standing on a vast spherical shoreline and tossing a pebble into the air. For that pebble to land precisely on a thin circular ring drawn on the ground beneath you would be rare. For a cosmic object to approach along the solar system's ecliptic, out of all possible angles, in a sky spanning billions of square degrees, would be rarer still. Yet that is exactly what 3I Atlas did. The alignment carried a quiet implication. If this was natural, then some cosmic process had sculpted its path into conformity with the architecture of our solar system. And if no such process could be identified, the alignment risked appearing almost intentional, even though science recoils from such conclusions without extraordinary evidence. The dynamicists who mapped its orbit did so with careful neutrality. They described the inclination, they measured the nodal orientation, they computed the perihelion passage, and each computation deepened the strangeness. The trajectory was not merely resting near the ecliptic, it glided directly within it as though it had been following the planetary plane for a long stretch before entering the inner system. But this presented another puzzle. If the object had been shaped by gravitational interactions within our system, if it had been pulled into the ecliptic by Jupiter, or shepherded by repeated solar passes, then astronomers would have expected to see evidence of such a history in its velocity profile. Instead, the object was incontrovertibly interstellar, its speed exceeding the grip of our Sun, its hyperbolic orbit unmistakable. It had not been bound to our system in the past. It had not been shaped by planetary influence. It had simply entered the solar system already aligned. One coincidence could be dismissed. Two coincidences demand caution. But three or more begin to whisper that the underlying assumptions may be incomplete. Oumuamua arrived at a moderate inclination. Borisov even more steeply. They behaved as interstellar objects should, scattered by the gravitational chaos of other systems, thrown into space with no regard for the tidy organization of ours. Atlas, however, floated in along the most improbable route, one that offered the highest observational accessibility for Earth-based telescopes. The alignment made it almost unavoidable. Its orbital path passed through regions continually monitored by spacecraft automated surveys and ground-based telescopes. This meant that Atlas would be subject to an unusually rich observational campaign. NASA's missions, amateur astronomers, and ground observatories would all intercept its trajectory with minimal obstruction. The solar system seemed to have arranged itself for this visitor's arrival. Yet if nature had orchestrated this perfect alignment, the mechanism behind it remained obscure. There are phenomena that flatten or guide trajectories, gravitational disks around newborn stars, gas clouds that shepherd debris, or interactions with planetary systems that compress orbital planes. But these forces operate near the system of origin, not tens or hundreds of light years away, in interstellar space. Once an object is flung into the void, its inclination becomes a fixed signature of its ejection. Interstellar space does not offer a convenient medium to realign or reshape orbital planes. There is nothing to nudge nothing to pull nothing to correct its course. So why did Atlas arrive with a trajectory so precisely tuned? A few astronomers proposed that the object might have been ejected along the plane of its birth star system, and by sheer coincidence that plane happened to coincide with the solar system's. This explanation was mathematically possible, yet statistically fragile. The galactic population of stars is oriented randomly with inclinations distributed in all directions. The idea that two unrelated planetary systems share near identical orbital planes is astronomically unlikely. Others suggested that Atlas may have passed close to another star during its long interstellar journey, receiving a gravitational nudge that altered its inclination. But the chance alignment required for such an interaction to steer it directly into the solar system's ecliptic would be even more improbable than its natural arrival. And so the puzzle remained neither dismissed nor resolved. The precision of its trajectory soon began to shape the narrative. For some researchers, it was a curiosity, an anomaly that would eventually collapse into a natural explanation once more data arrived. For others, it was the first hint that the object's origin story might be richer than the standard model of interstellar debris allows. And for a small number of theorists, it raised the provocative possibility that Atlas might not simply be debris at all, but rather a fragment of something shaped, however subtly, by processes not yet understood. To call it engineered would be premature. To call it coincidental would be evasive. Between those extremes lies the true essence of scientific mystery, a space where data resists simplicity, where interpretation demands humility, and where uncertainty becomes a form of invitation. As Three-Eyed Atlas slipped deeper into the solar system following its improbable course as though tracing a line drawn long ago, the alignment continued to hang over every observation. It was the quiet geometric anchor of the enigma, an elegant shape carved through space that defied expectation. And in its precision, some scientists felt the first stirrings of unease, as though the object had arrived not simply by chance but by some deeper orchestration written into the vast indifferent dark. The trajectory had spoken, and what it whispered was this: the universe had not finished surprising us. Even in the earliest attempts to sharpen its blurred contour, Three-Eyed Atlas resisted the simple act of being seen. Telescopes strained to impose structure upon it, to carve a boundary between object and void, yet every instrument returned the same ambiguous truth. A body wrapped in a luminous haze, a presence whose shape seemed to dissolve the moment observers tried to define it. In astronomy, shape is not merely aesthetic, it is diagnostic. It reveals rotation composition history. Yet with Atlas, the light refused to cooperate, spreading outward in a manner that suggested both diffusion and coherence, as though the object were cloaked in its own uncertainty, and uncertainty became the very architecture of its appearance. The initial images from ground observatories portrayed a smudged sphere of brightness, neither elongated like Oumuamua, nor sharp-edged like a classical comet nucleus. Even after NASA's data pipeline processed the earliest high-resolution frames, the result remained stubbornly indistinct, a glowing orb with no discernible silhouette. For many, this lack of clarity came as no surprise. Interstellar objects, especially faint ones, often defy the crispness of textbook imagery. But beneath that standard explanation lay a deeper tension. The blur was not behaving like normal cometary haze. A conventional coma, the cloud of gas and dust that envelops a comet when it approaches warmth, forms a predictable asymmetric structure. Solar radiation pushes dust outward. Jets carve streaks across the halo. The coma thickens in specific regions and thins in others. But Atlas showed none of these expected gradients. Its luminous envelope was eerily uniform, a smooth wash of light, as though engineered to hide whatever lay within. Even the brightest regions lack the sharp gradients typical of outgassing sources. To some astronomers, it looked less like a comet releasing material, and more like an object concealed behind a veil. Spectroscopic readings, though limited at this early stage, deepen the mystery. The light scattering from the object's surface did not align cleanly with the composition of known ices or dust grains. Some wavelengths appeared muted, others exaggerated, as if the scattering layer itself possessed unexpected properties. A few researchers speculated that the coma might contain unusually fine particulates, more reflective than typical cometary dust. Others suggested exotic volatiles sublimating in patterns unfamiliar to solar system models. But each hypothesis, when tested against the data, left questions unanswered, and questions multiplied. The brightness of Three-Eyed Atlas did not fluctuate as strongly as it should have for a rotating body. Most comets exhibit periodic brightening and dimming as jets activate on sunlit sides and fade in shadow. Irregular shapes produce rhythmic signatures in their light curves. Yet Atlas measured repeatedly pulsed, with a steadiness that implied something astonishing. Either its shape was unusually symmetric or its surface was behaving in a controlled uniform manner that defied the chaotic nature of natural outgassing. A perfect sphere was unlikely. Uniformly reflective coma, however, was possible, yet not in any familiar way. Astronomers attempted to peer deeper by modelling the object's scattering profile. If the object were elongated, the light curve should reveal subtle modulations. If it possessed a binary structure, two nuclei bound together, the brightness should hint at mutual shading effects. If dust formation varied by hemisphere, the object's rotation should sweep detectable changes across the halo. None of these models fit. The light remained stubbornly steady, as though the object were wrapped in a cloak that smoothed all imperfections. This uniformity became one of the early whispered puzzles within research circles. Was the object's halo a simple product of outgassing, or was it masking something beneath it? Something whose true form remained hidden behind a shroud of particles, arranged in a configuration that mimicked uniformity. One astronomer described its appearance as a lantern behind fog. Another compared it to observing a candle inside a frosted sphere. These metaphors captured the central frustration: the object was bright but not revealing, luminous but not informative. Beneath the sheen, the structure remained elusive. NASA in its official presentation offered the cautious explanation the haze was the expected visual texture of a natural comet. Yet even in understated terms, the agency acknowledged that the images were limited, inconclusive, and unable to resolve any fine-scale structure. This carefully neutral language belied a quiet truth, namely that the images did not meaningfully advance the classification debate. The shape remained an unknown variable in an equation already complicated by excessive mass, improbable alignment, and erratic behavior. Meanwhile, amateur astronomers, often working with remarkable ingenuity and powerful personal telescopes, captured independent images that revealed something more unsettling. In moments of temporary clarity, brief atmospheric openings in pristine night skies, some observers recorded faint linear protrusions emerging from the halo. These features resembled jets, yet, unlike normal comet jets, they were narrow, coherent, and unblurred by the object's rotation. They extended from the indistinct nucleus in lines too clean to be dismissed as photographic artifacts. What shape could exist beneath such jets? A rotating sphere should create sweeping smeared emissions. A tumbling irregular body should create chaotic arcs, but Atlas produced jets that seemed disciplined, steady, anchored to fixed points on an unseen surface. This was not the behavior of a fragment of ice disintegrating under sunlight. It suggested an underlying geometry, a stable structure directing emission along specific vectors. Still, the shape refused observation. Telescopes, both terrestrial and orbital, attempted deconvolution, sharpening algorithms, and frame stacking to pierce the glow. Yet every refinement ended the same way, an unresolved core concealed by a glow that seemed almost purposeful in its opacity. The frustration among researchers was not born of sensationalism but of physics. Shape informs density. Density informs origin. Without knowing the shape, mass estimates remain ambiguous, models of outgassing lose their grounding, and theories about the object's nature teeter on uncertainty. And with every failed attempt to capture a clear silhouette, the enigma grew. Some scientists suggested that the coma might contain nanograins particles so small they scatter light with near-perfect isotropy, eliminating shape-defining shadows. Others proposed that the object might be undergoing continuous microfracturing, releasing dust in such abundance that the nucleus remained permanently obscured. A few speculated about composite structures, perhaps a fractured object shedding material evenly across its surface. Yet none of these explanations accounted smoothly for the consistency of the glow, nor for its resistance to variation across observation sessions. Beneath the haze, something was there, something with jets, rotation, mass, and motion. But its true shape, the most basic of astrophysical descriptors, remained cloaked. In the unfolding portrait of 3I Atlas, this refusal to reveal form became one of its earliest and most persistent signatures. It was a visitor willing to share its presence, its light, its motion, but not its physical identity. And in that withholding, the object taught observers a quiet lesson: not all mysteries announce themselves through complexity. Some arrive veiled not to hide their nature, but to remind those who watch that clarity is not a guarantee when peering into the unknown. Before the scientific community had time to settle its thoughts around the unusual mass improbable trajectory and unresolved shape of 3 Atlas, another anomaly rose from the early observations, one so conspicuous, so visually startling, that even casual sky watchers could not help but feel its strangeness. The tail of the object, that iconic hallmark of cometary behavior, refused to obey the ancient choreography written by solar radiation and the heat of a star. Instead, it shifted, reversed, vanished, and reappeared in ways that suggested not a natural plume of dust, but something more deliberate, more intricate, and more perplexing. The earliest reports described a faint tail, normal enough though smaller than expected. But then came the first disruption. The tail disappeared. Not diminished, not altered. It simply vanished, leaving behind the unresolved halo but no downstream stream of dust. Days later, a tail reappeared, but it pointed in the wrong direction toward the sun instead of away from it. Astronomers labelled this a sunward anti-tail, a rare but not unheard of phenomenon caused by specific geometric alignments between dust orbit and viewing angle. Yet even that explanation struggled to contain the reality of what observers saw. For a brief period in July and August, the anti-tail stretched outward, like a luminous contradiction defying the instinctive expectation that solar radiation should push the dust away. Then, as though the object had changed its mind, the anti-tail faded again, giving way to a more traditional tail, but only momentarily. By late September, as the object drew closer to the sun, the tail vanished once more, leaving astronomers staring at a glowing core whose behavior resisted all simple interpretation. A comet is a creature of heat. It awakens when warmed, developing a tail as volatile ices sublimate into gas. but 3I Atlas acted like something whose thermal behaviour had been misinterpreted as if it were following a script only partially compatible with the physics governing ordinary cometary evolution. When the object emerged from solar conjunction weeks later, telescopes expected a standard post-perihelion plume, a bright, sweeping tail carried outward by solar wind. Instead, they found two structures, a renewed anti-tail and a newly formed tail sprouting simultaneously like twin signatures, produced by conflicting forces. The duality was peculiar. Traditional comets can exhibit multiple tails, but the geometry, timing, and coherence of Atlas's structures defied the predictable logic of dust and ion streams. The deeper puzzle lay not in the tails themselves, but in the behaviour of the outgassing. Amateur astronomers, often capturing images with astonishing clarity, recorded what appeared to be 7 jets, tightly collimated linear streams of material, extending almost 1,000,000 kilometres from the core. These jets were not diffuse as comet jets usually are. They were coherent, straight and unblurred, maintaining their shape across multiple nights of observation. And this created a paradox that rippled through the scientific community. The object was estimated to rotate once every 16 hours. Such a rotation should smear the jets into arcs or curves. The orientation of each jet should shift as the rotating nucleus exposed different vents to sunlight. Instead, the jets held their direction like fixed beams, as if attached to a body whose orientation did not change, or as if the jets were not tied to the rotation at all. In either scenario, the implication strained classical comet models. If the jets were fixed, then the body was not rotating, as predicted, a contradiction to earlier brightness variation calculations. If the jets were changing orientation but appeared fixed, then their emission must have been modulated to counteract rotation, something no natural mechanism is known to do. If the jets were detached from surface vents, perhaps magnetic structures or ion flows, then their narrowness and coherence remained unexplained. And if the jets were technological, as some speculative thinkers dared to suggest, then their behaviour would make sense. But such an assumption required evidence far beyond these early irregularities. The tension between interpretation and anomaly deepened. Jet formation is often chaotic. Sublimation creates jets when pockets of volatile ice erupt from beneath the crust, spraying dust and gas into space. These flows bend, soften, widen, and fluctuate. Over distance, they diffuse and broaden. But the jets streaming from the 3U Atlas were extraordinarily straight, clean lines, drawn across the void, their sharpness undisturbed by turbulence or rotational motion. Some astrophysicists argued that the jets could be ion streams shaped by solar magnetic fields, rather than physical plumes of dust. Yet even this theory struggled to account for the unchanging vectors of the jets. Solar magnetic fields vary continuously. They twist, ripple, and reconfigure under the influence of the solar wind. A jet controlled by such fields would drift. It would not remain fixed. Others propose that the jets originated from deeply buried reservoirs that erupted with unusual force, creating narrow, high-velocity plumes that remained coherent over long distances. But coherence at the scale observed nearly 1,000,000 kilometres was unprecedented, and such eruptions should have caused rotational wobbling or torque effects that were simply not detected. The tail behaviour too resisted simplification. The transitions from tail to no-tail, from anti-tail to dual-tail structure, implied a pattern of sublimation and dust dynamics that no existing model could replicate. If Atlas contained exotic ice's super-volatile substances activated only under specific temperature thresholds, it might produce sudden bursts or directional changes. But such materials would leave distinct spectral signatures, yet none were definitively found in the early data. The final puzzle was the timing of the tail's appearances and disappearances. These events did not align with expected thermal cycles. They appeared almost synchronous with geometric configurations, moments when the object's orientation relative to Earth and the Sun created symmetrical viewing angles. This pattern hinted that at least some of the observed anomalies might have arisen from optical geometry rather than intrinsic behaviour. Yet even this conservative interpretation failed to explain the rigidity of the jets, or the persistence of directional anomalies. The scientific community began to split, not in confrontation but in curiosity. One side leaned toward exotic but natural explanations, unfamiliar ices, unexpected dust grain, distributions, unusual nucleus geometry, or complex interactions between dust and the solar wind. The other side, more tentative, considered that the object might represent something not yet classified, something that blurred the boundaries between comet-asteroid and interstellar debris, something neither entirely natural nor directly indicative of advanced engineering, but occupying a liminal category where known physics remained insufficient. And a small careful group led in part by Avi Loeb raised the possibility that if nature could not comfortably explain these behaviours, then we must allow room, however small, for the idea that 3I Atlas might be more than debris. Not proof, but possibility. Through it all, the tale of Atlas continued its contradictions, appearing dissolving, reversing and recombining. A symbol not simply of sublimation, but of an object that defied being pinned into any conventional category. It was not yet clear whether 3I Atlas was a comet misbehaving or something else entirely, but its tail behaviour ensured that the mystery surrounding it would not fade. It would deepen. Long before most telescopes could resolve the faint shimmer of 3I Atlas models, predicted a simple, predictable truth: an object of its estimated size, illuminated by a distant star and warmed by solar proximity, should rotate with periodic variation. That rotation, clocked at approximately 16 hours, should twist any jets of outgassing material into graceful spirals or wide diffuse arcs, each shaped by the turning of the nucleus beneath. This rhythm is common among comets. Their vents open and close under shifting sunlight, producing irregular pulses of material that trace the hidden geometry of their turning bodies. But 3I Atlas refused to participate in this ancient cosmic dance. From the first independent images captured by amateur astronomers, those rare, pristine frames, preserved from dark mountain tops and cold desert skies, observers noticed something deeply unusual. The object appeared to emit jets, narrow linear streams of material, extending outward in clean, coherent lines. Not one or two, but 7 distinct jets, each one faint yet unmistakably structured. They stretched across space like luminous threads drawn tight from the core into the darkness. Their brightness varied slightly, but their orientation did not. The jets pointed in fixed directions, as though anchored to immovable positions on an unseen surface. And this was the first contradiction. A nucleus rotating every 16 hours should drag these jets along its surface, sweeping them through space like the trails of a rotating sprinkler. The narrowness of the jets should cause them to arc, curve and twist. Their orientation should shift at predictable intervals. But in every observation, night after night, instrument after instrument, the jets remained steady. They did not smear. They did not widen. They did not drift. They held their direction with a precision no ordinary comet could maintain. This was not simply unexpected, it was unprecedented. Traditional comets displayed jets shaped by randomness vents. Open irregularly, thermal fractures erupt without pattern dust plumes scatter under solar wind perturbations. Jet direction changes as the nucleus turns, and even strong jets bend after a few thousand kilometers. But Atlas's jets extended almost 1,000,000 kilometers into space without distortion, a length more typical of ion streams, yet too sharply defined to match ion tail diffusion. Their structure suggested collimation, the process by which a beam remains narrow instead of dispersing. On Earth, collimation is a property of engineered systems, lasers, thrusters, particle beams. In nature it is rare, and at the scale observed in Atlas it borders on impossible. Astronomers were careful, methodical and cautious in their interpretations. Many proposed that magnetic fields might have shaped the jets. Solar magnetic structures can channel ionized particles into narrow streams. But those structures are unstable, shifting under the influence of solar wind turbulence. A jet guided magnetically would sway, ripple and drift, not remain locked into an unchanging vector for days on end. Another explanation suggested that sunlit surface regions might release material along fractures that happened coincidentally to align in ways resistant to rotation. But given the object's mass and hypothesized rotational speed, such fixed features should produce torque rotational wobbling, causing the jets to eventually skew or distort. Yet there was no sign of precession, no sign of rotational drift, no observational evidence of changing orientation. In every frame the jets pointed outward like unwavering signals. This stability, when combined with their length and narrowness, formed one of the most confounding anomalies associated with 3I Atlas. The jets were not only coherent, they were disproportionately straight, resisting the natural widening expected from dust-driven plumes. The physics of dust expansion demand divergence. Particles travel outward with varying velocities, dispersing naturally into a conical spray. But the jets of Atlas seemed constrained, as though held together by some external structure, or guided by forces not normally active in cometary environments. Researchers began examining multi-night exposures to look for subtle oscillations. A drift of even a few arc seconds would have suggested natural variability. but the jets held their lines with precision that appeared indifferent to the object's rotation. This raised an uncomfortable question: were the jets actually emerging from the nucleus at all? Or were they perhaps the result of internal processes obscured by the luminous haze processes, unlike the simple sublimation that drives ordinary cometary jets? Some astrophysicists posited the possibility of deeply buried vents releasing gas at extremely high velocities, producing beams with enough kinetic focus to resist dispersion. Yet the energy required for such outflow would be immense, far beyond what solar heating could produce at the object's distance. Others considered exotic ices volatile compounds capable of sudden, efficient sublimation that might create collimated flows. But spectral readings did not show the clear signatures of known supervolatile species, and even such exotic substances would struggle to maintain narrowness over million-kilometre distances. Then came the most speculative interpretations, whispered, hesitant, and often spoken with a caveat of caution. If the jets were not the byproduct of sublimation, then what were they? Were they rotational anomalies? Ion beams? Charged particle streams driven by internal processes? Or something else entirely, something that hinted at artificial mechanisms? These were not mainstream hypotheses. Most researchers dismissed them outright, but the persistence of the anomalies left the conversation open in a way few expected. If the jets were artificial, their consistency would make sense. If they were thruster emissions-controlled directional outflows from an engineered device, they would naturally align with fixed vectors. They would not smear with rotation because the emission source would remain steady relative to the object's inertial frame. And their narrowness, their length, their improbable coherence, each would fall neatly into place under such an interpretation. Yet science cannot leap to extraordinary conclusions without extraordinary evidence. And so the community returned repeatedly to the framework of natural explanations, even when each attempt left gaps wide enough to expose the underlying puzzle. Why did the jets not drift? Why did rotation not influence them? Why did their lengths exceed known natural jet stability limits? And why did they appear in a configuration so symmetrical, so organized, that even statistical modeling struggled to replicate it under random conditions? As the data accumulated, one truth became increasingly clear: the jets of 3R Atlas were among the object's most distinctive features and among its most confounding. They were not easily dismissed as photographic artifacts. They were not noise. They were real structures in space extending across vast distances with unnatural discipline. For many researchers, the anomaly did not suggest alien technology. It suggested something perhaps even more compelling: that nature in its vastness might possess modes of structure and behavior not yet catalogued by human observation. The cosmos is not obligated to match our expectations. And 3E Atlas, with its unwavering jets pointing like silent beacons into the void, became a reminder that the universe sometimes introduces objects whose physics challenge the boundaries of current understanding. In the growing mystery surrounding Atlas, the fixed jets were no longer a minor feature. They were a declaration, one carved across 1,000,000 kilometers of space, visible to those who cared to look closely, pointing toward deeper enigmas just beginning to unfold. By the time the first coordinated datasets from ground telescopes, NASA archives, and independent astronomers were compared side by side, it became clear that what surrounded 3I Atlas was no ordinary puzzle but a tapestry of irregularities, each thread inexplicable on its own, yet even more confounding when woven together. It was not the presence of one anomaly that unsettled researchers, it was the pattern of them. The objects seemed to behave as though every familiar rule of cometary physics applied only partially or only intermittently, or in ways that resembled known processes just enough to mimic them, but never enough to fit comfortably within them. Avi Loeb, who had long argued that interstellar objects require new categories of analysis, enumerated 12 major anomalies, an outline that circulated quietly among academics and loudly among the public, becoming a catalyst for debate. These anomalies, drawn from early observations and cross-verified by multiple independent sources, formed a framework that scientists could neither dismiss nor fully explain. The first was the mass so disproportionate that the very statistics of interstellar debris faltered beneath it. If 3 Hysatelus was truly hundreds to thousands of times more massive than any previously observed visitor from beyond the solar system, then the cosmic population of large interstellar bodies was either wildly misunderstood, or this object was unique in its scale. The second anomaly lay in its trajectory, aligned so precisely with the solar system's ecliptic that the odds of such an arrival occurring naturally were vanishingly small. This was not a casual tilt or a modest coincidence. It was a nearly perfect alignment, as if the object had drifted in along the straight edge of an architect's drawing, choosing the path of maximum visibility. The third anomaly resided in the object's shape, or rather the refusal of its shape to reveal itself. Despite increasingly sensitive imaging, the core remained obscured behind a luminous haze, one too uniform, too consistent to match classical coma behaviour. The brightness curves held steady, far beyond what a rotating irregular nucleus could justify. This uniformity suggested either a nearly perfect spherical body, rare among comets, or a coma whose properties smoothed every irregularity with uncanny precision. The fourth anomaly was its thermal behaviour. Interstellar comets often flare when warmed, awakening under solar radiation in bursts of activity. But Atlas behaved more like a hesitant organism, its tail switching on and off with no fidelity to temperature cycles. Sublimation, that most fundamental engine of cometary activity, seemed to act at times and vanish at others, as though governed by conditions not fully tied to heating. The fifth anomaly, the tail itself, carried contradictions, disappearing entirely for days, then reappearing in reverse, forming an anti-tail during months when such geometry was mathematically possible yet still rare, then once again dissolving only to return paired with a conventional tail. No known comet had ever displayed such a sequence of tail inversions with this precision and timing. The sixth anomaly lay in the jets, those narrow beams that stretched into the void with unnatural coherence. The object's rotation should have smeared these jets into arcs. Instead, they remained fixed. 7 jets emanating from 7 anchored points, unaltered by orientation or spin, defied the physics of natural outgassing. Their lengths alone, approaching 1,000,000 kilometers, placed them among the strangest features ever recorded in a comet-like body. The seventh anomaly puzzled dynamicists, the lack of rotational modulation. Objects of comparable size exhibit distinct light curve oscillations as sunlight sweeps across irregular surfaces. Atlas's light curve, however, remained unexpectedly smooth. Even the most accommodating models failed to replicate its stability without invoking improbable shapes or dust distributions. The eighth anomaly was chemical. Early spectroscopy revealed signals that hinted at gases and dust, but the mixture did not align cleanly with those of typical comets. If exotic ices were present, they were either masked by noise or existed in ratios unfamiliar to the solar system's inventory. This perplexed those who had expected a comet formed around another star to reveal unique chemistry but not ambiguity. Instead, Atlas offered spectral hints that contradicted themselves like a fingerprint smudged before it could be compared. The ninth anomaly came from its deceleration or lack thereof. Oumuamua had accelerated away in a manner consistent with radiation pressure, acting upon a thin surface. Borisov decelerated as expected for a natural comet shedding mass. Atlas, however, maintained a motion that neither displayed the typical seeds of non-gravitational acceleration, nor conformed precisely to models of purely gravitational motion. The discrepancy was subtle but real, a small whisper in the equations suggesting something beneath the noise. The 10th anomaly involved the object's onset of activity. It became active earlier than expected for a comet at its distance from the Sun, then became inactive when it should have awakened further. Traditional volatiles cannot explain such inverted timing. If the object contained deeply buried reservoirs, their activation patterns would differ, but not in a way that fully matched the observed cadence. The 11th anomaly concerned fragmentation, or rather the absence of it. Massive comets approaching the Sun's heat often fracture, yet Atlas remained cohesive, its jets fierce and its halo luminous, but its nucleus steadfast. The internal strength implied by this stability would require a structure more resilient than the loosely bound conglomerates typical of cometary material. The 12th anomaly was observational. Atlas seemed consistently easier to detect than its brightness alone justified. Whether by coincidence or by intrinsic properties, its visibility in multiple wavelengths surpassed expectations. It was as if the object made itself noticeable not through intent, but through a combination of features that amplified its detectability across instruments. Taken individually, any one of these anomalies might have been dismissed as noise error, or the benign quirk of an unusual comet. But taken together, they formed a pattern that strained the boundaries of classification. The object was too massive to be typical, too aligned to be random, too veiled to be normal, too disciplined in its jets to be natural, too contradictory in its tail to be predictable, too chemically ambiguous to be understood. And collectively, these anomalies created a portrait that was not simply strange. It was dissonant, not alien, not artificial, not definitively extraordinary. but dissonant like a rogue note in a composition whose harmony depends on the quiet obedience of celestial mechanics. 3i Atlas in its silent descent had begun to reveal itself, and what it showed was a visitor made not of one mystery, but many, each inviting humanity to look closer, question deeper, and accept that the universe still holds objects whose purpose, nature and origin lie just beyond the reach of current understanding. Long before the new images were unveiled, long before NASA stepped before the public with its polished livestream and scripted explanations, a quiet expectation had been building across the scientific community. Researchers, journalists, and casual skywatchers alike hoped that the agency would seize this moment, the arrival of only the third confirmed interstellar object, as an opportunity to acknowledge the extraordinary. They hoped for a recognition that 3 Atlas was not merely a dusty wanderer drifting into the solar system, but a visitor wrapped in puzzles carrying contradictions that deserved transparent discussion. Instead, the official tone was measured to the point of restraint. NASA's presentation began with the familiar cadence of cautious certainty. The object was described as a comet. Its behavior, according to the agency, fit broadly within the spectrum of cometary activity, albeit with some unusual characteristics. The new images displayed during the livestream's soft blurred contours consistent with previous releases did little to clarify any of the anomalies that researchers had been discussing for months. Despite anticipation, the pictures revealed no new structural detail, no refined silhouette, no decisive evidence of jets or fragmentation or rotational modulation. They were, in the words of several analysts, safe. That safety, however, came at a cost. For many who had followed the unfolding mystery, NASA's approach felt less like an exploration and more like a reassurance, a reiteration of the familiar narrative that interstellar objects, despite their unusual origins, should be interpreted through the lens of known physics. This caution was not new. Since the controversy surrounding Oumuamua's acceleration, the agency had favoured interpretive conservatism, prioritising established models over speculative inquiry. Yet with Atlas, this tendency to default to simplicity appeared increasingly strained, as though the complexities of the object were being pressed into a framework that no longer held. The timing of the announcement added another layer to this tension. NASA noted that data processing had been delayed due to the government shutdown earlier in the year. While this explanation was factual, it also implicitly framed the livestream as a logistical update rather than a scientific turning point. But for those who had hoped for deeper commentary on the object's anomalies, the delay felt symbolic, an extension of the institutional hesitation to confront the unexplained directly. In interviews surrounding the event, Avi Loeb articulated the frustration shared by many independent researchers. His critique was not rooted in sensationalism, but in a philosophical philosophy of scientific openness. Where NASA offered broad reassurances, Loeb pressed the need for specificity. Where the agency downplayed anomalies, he enumerated them. And where officials framed Atlas as a variant of known cometary behaviour, he highlighted the ways in which the object resisted this classification. Loeb's concern was not that NASA misinterpreted the data, but that it avoided the deeper questions the data posed. Why was the mass so extreme compared to previous interstellar objects? Why had no similarly massive visitor been detected before? Why did the object's trajectory align with the ecliptic plane so precisely? Why did the tail behave inconsistently, disappearing and reversing in ways that contradicted expectations? Why did the jets remain narrow and fixed despite the object's rotation? These questions were scientifically legitimate. They did not imply alien intelligence. They did not assert artificial origin. They simply pointed to gaps in understanding, gaps that deserved acknowledgement rather than circumvention. But institutional caution is a powerful force. NASA's mandate is not speculation, but consensus. The agency operates within a landscape of political scrutiny, public expectation, and scientific accountability. To propose that an object might be more than a comet even hypothetically risks misinterpretation, sensational headlines, and misplaced fears. And so the agency framed its findings within the most conservative interpretation available. 3i Atlas was a natural comet, consistent with known behaviour, its peculiarities explainable by variations in dust angle and illumination. To NASA, this approach was a responsible act of scientific communication. To many observers, it felt like a missed opportunity. The dissonance emerged not only from what NASA said, but from what it did not say. The livestream made no mention of the 12 anomalies outlined by Loeb. It did not address the unusual mass, the trajectory alignment, or the fixed jets. It did not discuss the chemical ambiguities or the inconsistent tail formation. The agency's silence created an interpretive vacuum, one filled quickly by debate, speculation, and renewed scrutiny of the object. Behind this public moment lay a deeper truth about institutional science. Agencies often feel compelled to present a unified stance, even when internal discussions are more complex. It is easier to offer a simple explanation than to defend uncertainty, easier to reassure than to provoke, easier to categorize than to admit the limits of current knowledge. This preference for simplicity is not unique to NASA. It is woven through the entire culture of scientific communication. Yet interstellar objects expose the limitations of that culture. They arrive from environments radically different from our own. They carry histories shaped by forces we cannot yet measure. They challenge assumptions about the distribution of matter in the galaxy. To treat them as mere outliers risks overlooking the deeper stories encoded in their behavior. Still, caution has advantages. By anchoring its interpretation in natural explanations, NASA maintained coherence with the broader scientific framework. The agency avoided the pitfalls of premature speculation. It upheld the principle that extraordinary claims require extraordinary evidence. And for many researchers, this restraint provided a stabilizing influence in a period marked by competing theories and public fascination. But even as NASA offered its measured conclusion, something unspoken passed through the scientific community, a recognition that the story was not complete. The data was not yet fully analyzed. The object was still approaching. Higher resolution images from Hubble, from Webb, and from ground-based observatories would soon reshape the conversation. And all the clarity NASA attempted to offer could be overturned by the influx of information expected in the coming weeks. In this sense, the livestream became a pause, a moment of incomplete resolution suspended between uncertainty and discovery. It was not the end of interpretation, but the beginning of a deeper tension between institutional caution and scientific curiosity. For while NASA's official stance was simple, the object itself remained anything but. 3I Atlas moved silently along its improbable path, unaffected by human interpretation, carrying its mysteries deeper into the solar system. And as it approached the moment when its secrets would become either undeniable or dissolved into new ambiguities, both NASA and independent researchers found themselves waiting, each with a different vision of what the universe was preparing to reveal. As 3I Atlas slipped deeper into the inner solar system, the world's instruments, all those mechanical extensions of human curiosity, began to turn toward it with increasing precision. What began as a faint unresolved blur soon became the focus of a coordinated observational campaign, spanning hemispheres, wavelengths, and technologies. It was a rare alignment spacecraft orbiting Earth telescopes mounted on volcanic summits, wide-field survey arrays scanning each clear night, radio observatories listening for faint emissions, all converging upon a single object drifting silently through space. If the early images were frustrating in their opacity, the growing arsenal of tools now trained on Atlas promised something more clarity, or at the very least the possibility of it. The Hubble Space Telescope, despite its age, brought a level of sensitivity unmatched by ground-based instruments. Its view above Earth's atmosphere allowed it to isolate the faint halo around Atlas with minimal interference. Observers hoped its sharp vision would finally penetrate the luminous coma and reveal the nucleus hidden within. But when the first Hubble frames were processed, the results continued the uneasy trend. The object remained unresolved. A bright core, yes, but still smothered in a luminous envelope that scattered light evenly. No edges, no contours, only the same luminous fog that had perplexed earlier observations. Then came the James Webb Space Telescope with its exquisite infrared sensitivity. If Atlas contained exotic ices or unusual chemical compounds, Webb's instruments would detect their spectral fingerprints. Its observational window, positioned far from Earth's thermal noise, offered an opportunity unmatched by any telescope before it. Scientists anticipated that Webb's spectrographs capable of splitting light with astonishing precision would reveal the presence of carbon chains, ammonia hydrates, or other volatiles not typical of solar system comets. But the early Webb spectra sparked more questions than answers. Certain wavelengths indicated the presence of expected molecules, water, ice, carbon dioxide, dust. Yet these signals were faint, incomplete, or inconsistent across multiple observations. Other wavelengths hinted at compounds not commonly seen in comets, possible organic fragments or unusual molecular structures, but none were strong enough to present a clean identification. The chemical portrait of 3I Atlas became a diffuse silhouette, neither confirming nor denying exotic origins. Ground-based instruments contributed a different perspective. The Atacama Large Millimeter Submillimeter Array, ALMA, perched high in the Chilean desert, probed the object's dust signature. By measuring emissions in submillimeter wavelengths, ALMA could map the distribution of dust grains and infer the temperature of the coma. Its measurements suggested an unusual distribution dust that was both too fine and too uniformly dispersed to match typical cometary patterns. This uniformity once again echoed the visual haze observed earlier, reinforcing the idea that the coma was not shaped by chaotic outgassing, but by something more stable, more structured. Meanwhile, a quieter class of instruments began their work, spectroscopic arrays designed to measure Doppler shifts. By analysing the subtle changes in frequency as Atlas emitted or reflected light, astronomers could determine the object's rotation and, more importantly, detect any non-gravitational accelerations. These measurements mattered immensely. If Atlas behaved like Oumuamua, showing slight accelerations inconsistent with gravity alone, it would hint at outgassing or radiation forces or something more unusual. Yet the Doppler data returned a puzzling ambiguity. There was no significant acceleration, but neither was there a complete absence of anomalous motion. Instead, observers noted tiny inconsistent deviations small enough to be attributed to measurement noise, yet persistent enough to suggest something at work beneath the threshold of detection. If these signals were real, they implied forces acting upon the object that were not correlated with visible outgassing. If they were noise, then the object remained gravitationally pure. The uncertainty hovered like a thin fog over every calculation. The Very Large Telescope VLT in Chile and Keck Observatory in Hawaii both attempted high-resolution imaging using adaptive optics to correct for atmospheric distortions. Their sharp insights captured faint streaks around the object's possible jet traces, yet once again the images raised as many questions as they answered. The jets appeared unnervingly straight, consistent with earlier amateur imagery, and their positions remained stable night after night. The coordinated international effort intensified. Astronomers initiated a global observation campaign, synchronized observations across continents. Cross-calibrated spectra stacked imaging sequences and time series photometry designed to catch any flickering that might betray the nucleus's rotation. But the photometry returned a nearly flat line. A comet of this size should pulse in brightness as it turns. Atlas, however, glowed with stubborn uniformity like a lantern held steady against the dark. And then there were archival searches where astronomers combed through old survey images hoping to find earlier glimpses of 3 White Atlas before it was officially discovered. If such pre-discovery images existed, they could refine the object's orbit, constrain its past motion, and rule out unusual accelerations. But so far, these archival hunts yielded no reliable pre-detection images. Atlas had entered the cosmic stage suddenly without historical trace, a visitor appearing from night with no recorded path behind it. Despite the growing web of observations, one truth became increasingly clear: human instruments were beginning to strain. The more data collected, the more the mystery grew. The instruments were not failing, they were performing exactly as designed. It was the object itself that refused categorization. Still, the tools kept probing. Hubble sought sharper edges, Webb sought clearer chemical lines, ALMA sought dust patterns, Keck sought rotational signatures, VLT sought jet morphology, radar arrays sought structural echoes, photometric campaigns sought periodicity. Piece by piece, the observations began to map the unknown, not fully, not cleanly, but with an accumulation of detail that hinted at structure beneath confusion. The picture forming was incomplete, but coherent enough to suggest that Atlas was not simply a comet behaving strangely. It was something more layered, something whose identity emerged only in fragments. Science, despite its tools, remained in the dark, but that darkness was beginning to take shape. By the time the first major wave of observations had been processed, astronomers found themselves confronting a reality both humbling and unsettling. Every established model proposed to explain 3Y Atlas seemed to break upon contact with the data. The object existed at the crossroads of contradictions too massive to comport with interstellar debris statistics, yet too inconsistent to belong comfortably among comets, too stable in its jets to match natural outgassing, yet too diffuse in its appearance to resemble anything engineered. In this ambiguity, the models mathematical, physical, and conceptual began to crack. The first and most obvious framework to test was classical comet physics. This model rests on a simple principle: when frozen volatiles heat under sunlight, they sublimate, producing jets that generate visible signatures and even non-gravitational accelerations. If Atlas was a comet, then sublimation should have explained the disappearing tail, the erratic antitail, and the linear jets. But sublimation creates chaos, not discipline. Standard comet jets spread into widening cones. They flicker, widen, bifurcate. They do not maintain million-kilometre straight lines. And the rotational modulation of a 16-hour period, if it existed at all, should have woven the jets into spiralling threads. Yet Atlas did not spiral. It held steady. Worse still, canonical sublimation demands thermal consistency. When the sun warms, the nucleus activity increases. When the object retreats, activity decreases. But Atlas's tail appeared and disappeared in defiance of thermodynamics awakening at strange times, fading when it should have grown and reversing direction in spans too short for natural dust realignment. The comet model, though adaptable, bent only so far before breaking. A second framework turned to interstellar comet analogues, taking lessons from 2I/Borisov, the first interstellar comet discovered. Borisov behaved almost perfectly according to expectations, outgassing, strongly fragmenting, under solar heating shedding carbon chains, typical of a comet formed around another star. If Atlas were an analogue, it should have displayed chemical signatures of exotic ice's CO, CN, C2 oxygen-bearing compounds. Yet the chemical lines from Webb and the ground-based spectrometers did not match Borisov's profile. Instead, the signals fluctuated across observations as though the coma composition were changing or masked, and so the analogue model too collapsed. Physicists then turned to a different family of hypotheses non-gravitational forces. Perhaps radiation pressure dust drag or ion interactions were shaping Atlas's path. This had been the explanation proposed for Oumuamua, its strange acceleration potentially caused by a thin, sail-like geometry. But Atlas was far too massive to be affected by radiation pressure in any meaningful way. The object's luminosity to mass ratio was simply too low. To accelerate Atlas, sunlight would need to push a mountain with the force of a whisper. Alternatively, perhaps the jets produced measurable thrust, subtly altering the object's trajectory. If so, scientists should have detected clear deviations from gravity-only motion. But Doppler analysis revealed only ambiguous, inconsistent micro-variation signals that refused interpretation. They were too weak to confirm thrust, yet too persistent to dismiss. Thus, the non-gravitational models withered. A fourth class of interpretation examined exotic chemistry. Perhaps Atlas contained supervolatiles ices that sublimated extremely low temperatures. These could explain some early activity far from the sun. But exotic ices still obey heat gradients. They do not appear and vanish in defiance of expected energy absorption. And they certainly do not produce collimated jets unless constrained by geometry that remained unseen. Next came fragmentation models. Many comets fragment under stress, shedding pieces that can cause sudden changes in jets and tails. But fragmentation leaves signatures, multiple cores, debris fields, brightening events. Atlas, despite its anomalies, remained whole. The fixed jets suggested structural consistency across weeks of observation. Fragmentation could not explain stability. Other models approached the problem from a purely geometric angle. The anti-tail could be explained by dust sheets oriented along the orbital plane. The disappearing tail might result from sunlight scattering at specific angles. But these models, elegant though they were, could only address one or two anomalies at a time. None explained the jets. None explained the coherence of the coma. None explained the mass. Geometry alone could not rescue the theory. As these frameworks faltered, some theorists ventured into the realm of interstellar origin hypotheses shaped by unfamiliar formation environments. Perhaps Atlas had formed near a dying star, its materials hardened under radiation. Perhaps it had passed through regions of space rich in magnetic turbulence, imprinting unusual grain distributions. But every attempt to imagine an extreme birthplace eventually encountered the same problem. Atlas's anomalies were not purely chemical, nor purely physical, nor purely dynamic. They were everything at once, layered, interdependent, and inconsistent with the patterns expected from natural history alone, and so the community reached a kind of philosophical crossroads. Some chose the position of elastic naturalism, insisting that no matter how many anomalies Atlas presented, they must have natural explanations, ones not yet discovered perhaps, but discoverable. In this view, Atlas became a teacher, a body whose complexity reveals the inadequacy of existing models, pushing planetary science toward new equations, new theories, and new humility. Others adopted a cautious but more speculative viewpoint, the hybrid model. In this perspective, Atlas might be natural in composition, but unusual in structure, perhaps a fragment of a disrupted exoplanet, a chunk of crystalline mantle material, or a piece of recondensed ejecta formed under pressures not common in our own system. This could explain its mass stability and resistance to fragmentation. It could even help with the jets if the surface contained fissures aligned through ancient tectonic stresses, but even this model strained under the fixed directionality of the jets. Then came the model that many avoided, but none could fully dismiss the technological hypothesis. Not as a claim nor as a conclusion, but as a lens and interpretive tool. If Atlas were artificial, the anomalies solved themselves. Fixed jets could be thrust. Tail reversals could be emissions. Uniform luminosity could be a controlled surface. The mass could be structural. The alignment with the ecliptic could be intentional. But without supporting evidence metallic spectroradio emissions geometric silhouettes, this hypothesis remained a philosophical outlier present only in whispers at the edge of scientific dialogue. What made the situation extraordinary was not that one model failed, but that all did. Each broken hypothesis left behind a fragment of truth yet failed to assemble the full picture. And like the shadowed core hidden beneath Atlas's glowing veil, the deeper structure of the mystery remained concealed, even as layers of interpretation peeled away. In the end, the modelling effort illuminated not what Atlas was, but what it was not. It was not a typical comet. It was not a fragment behaving predictably. It was not consistent with any single discipline: chemistry, physics, dynamics, or geometry. It sprawled across them all, touching each but belonging to none. This was the point at which theory began to give way to awe, the acknowledgement that the universe, vast and ancient, does not always conform to its observers' expectations. And in that recognition, the mystery of 3i Atlas only grew deeper, preparing to confront humanity, with even stranger implications as it continued its silent descent. Long before 3i Aeolus carved its shimmering line through the solar system, the scientific world had already been shaken by the revelations surrounding Oumuamua, its unexplained acceleration, its absence of coma, its peculiar geometry. Those debates carved a fault line that still runs through contemporary astrophysics, the divide between extreme naturalism, the insistence that all cosmic objects must conform to known laws, and the quiet, more daring suggestion that perhaps the universe occasionally delivers something engineered. Not by humans, of course, but by some distant intelligence whose technological fingerprints linger faintly in phenomena we struggle to interpret. With Atlas, that speculation, carefully avoided by institutions yet quietly explored by independent theorists, began to return not as a headline but as an intellectual whisper. Possibility, a lens through which some of the object's most resistant anomalies could be viewed with coherence rather than contradiction. The technological hypothesis did not begin with claims, it began with questions. What kind of natural object maintains 7 fixed jets that refuse to drift with rotation? What natural mechanism creates near-perfect coma, uniformity, bright enough to hide the nucleus indefinitely? What random visitor arrives along the solar system's planetary plane? The very geometry that maximizes detectability. What interstellar fragment possesses a mass so extreme that it contradicts the expected distribution of cosmic debris? No single anomaly implied anything extraordinary, but taken together the pattern began to press against the edges of what nature as understood through existing models could plausibly produce. Avi Loeb, one of the leading voices advocating for the inclusion of technological possibilities in astrophysical interpretation, framed the issue in familiar terms. Just as artificial satellites in Earth orbit can be mistaken for asteroids when viewed without context, so too might extraterrestrial technologies masquerade as natural objects when observed at interstellar distances. Not as a claim, but as a methodological reminder that the training dataset of astronomers includes only one example of advanced engineering, our own. In that dataset, beams, radiators, sails, and exhaust plumes produce signatures that mimic natural processes only superficially. A hydrogen thruster can resemble a gas jet. A reflective hull can resemble a bright coma. A stabilizing mechanism can mask rotation. A controlled trajectory can appear improbably aligned. For the technological hypothesis, these parallels are not proof, merely the suggestion that some anomalous patterns may be more easily explained by design than by chaotic processes. One of the most compelling clues in the eyes of some theorists lay in the jets. Natural comet jets governed by rotational physics widen rapidly, but the jets of Atlas remained steadfast, narrow, and precisely aligned. In engineering, the term collimation refers to tightening a beam into a narrow, unwavering line, the principle behind lasers, particle streams, and thruster plumes. Natural collimation is possible, but extraordinarily rare, and never to the degree of stability observed in Atlas. If Atlas were a derelict, fragmented, or long deactivated technological structure, perhaps a remnant drifting across the galaxy, its jets could be the final traces of sublimating propellant chambers, directional vents, or engineered channels designed to channel material along fixed paths. The uniform haze surrounding its core could be a cloud of disintegrating insulation or shielding materials scattering light evenly and obscuring the underlying structure, and the mass so much greater than that of Oumuamua or Borisov could be explained by composite materials frameworks or compartmentalized structures capable of surviving interstellar transit. Natural fragments of such scale do exist, but their rarity makes Atlas's appearance as the third interstellar visitor improbable. An engineered object, by contrast, would be shaped by reasons unrelated to natural distribution's function, purpose, durability. But if 3 Atlas were a technological relic, then what was its purpose? Here speculation multiplies. Perhaps it was once a probe powered long ago, now fading into cosmic entropy. Perhaps it was debris, a remnant shattered from a megastructure orbiting a distant star. Perhaps it was not a vehicle, but a fragment of a larger technological entity, a beam, a shell, a panel, a collapsed segment of something vast. Or perhaps it was none of these things. The hypothesis does not require intent. It requires only structure that natural processes struggle to produce. Yet if there was one anomaly that lingered with particular force, it was the trajectory alignment. A random interstellar object should approach from a steep angle drawn by the gravitational whims of the galaxy. But Atlas drifted in along the ecliptic plane, the very geometry that maximizes observability by Earth's telescopes. If an ancient technological object drifted through interstellar space, its trajectory, shaped by its launch or by the dynamics of a distant star system, might preserve the imprint of design. A piece of engineering does not wander randomly, it follows a history. In the technological hypothesis, Atlas is not a functioning machine nor a vessel bearing signals or meaning. It is the cosmic equivalent of archaeological debris, a shard travelling through the void, weathered by time, stripped of context, reduced to anomalies seen from afar. Its behaviour, though strange, would reflect the remnants of internal structure, the rigidity of its jets, the stability of its coma, the resilience of its form. Still, the scientific community remains cautious. Extraordinary claims require extraordinary evidence, and Atlas offers none, not explicitly. It provides hints, patterns, and contradictions. But it does not reveal metal radio signals, circuitry, or symmetry. The hypothesis remains a fringe framework, not discredited but not embraced. It exists in the space between curiosity and discipline. For some, that space is precisely where progress begins. For others, it is where caution must prevail. Yet in the broader cosmos, technological possibility is not radical. The galaxy contains hundreds of billions of stars, many host planets. Some planets endure long enough for life to arise. A few may have reached engineering maturity millions or billions of years before humanity formed its first languages. If so, relics drifting across interstellar space are not only possible, they are inevitable. And should such a relic cross our path, it might not announce itself with symmetry or signals. It might look instead like 3 Atlas, a blurred core, a uniform glow, a set of fixed jets, an improbable trajectory, and a suite of anomalies that nudge the imagination toward questions science is only beginning to permit itself to ask. In this light, the technological hypothesis does not stand as a conclusion, but as an open door, a reminder that the universe's oldest artifacts may not resemble machines at all, but enigmas mistaken for comets. Long before 3 Atlas entered the solar system, astrophysics had already accumulated a vast library of theoretical landscapes, entire universes of possibility built to explain the strange, the rare, and the unprecedented. Yet even these frameworks, sprawling and imaginative as they were, struggled to contain the peculiarities of this interstellar visitor. As scientists wrestled with contradictory data and uncooperative models, they began to explore wider conceptual territories, searching for explanations that bridged the gap between known physics and the elusive behaviour unfolding before them. These explanations were not wild conjectures. They were extensions of established theories, speculative yes, but grounded in the quiet rigour of astrophysical thought. The first of these broader ideas came from non-gravitational dynamics beyond sublimation forces, invisible yet powerful enough to influence motion in subtle ways. Perhaps Atlas was responding to charged particle interactions within the heliosphere. Interstellar objects occasionally carry remnant magnetization from their birth environments, acquiring electrical charges as they drift through cosmic plasma. The solar wind could exert Lorentz forces on such an object, nudging its path in ways that mimicked anomalous jets or inconsistent accelerations. But while this idea held promise, the data's quiet inconsistencies resisted clean interpretation. The variations seen in Atlas's motion were neither strong nor coherent enough to map neatly onto magnetic models. A second avenue of speculation turned toward microfracturing physics. Interstellar debris experiences extremes of temperature, pressure, and radiation over millions of years. Some theorists suggested that Atlas's interior might have developed networks of crystalline fractures, thin channels through which sublimation gases could escape in unnaturally straight lines. If the interior contained exotic ices arranged in stratified layers, sublimation could occur along structural planes rather than chaotic pores. These fracture-guided plumes might produce the startling collimation of Atlas's jets, but this framework faltered when compared against the object's rotation. Even if microfractures directed jets into narrow streams, the 16-hour rotation period should have smeared them across the coma. The stability of the jets remained unexplained. Perhaps then the answer lay not in structure but in chemistry. Interstellar ices forged in environments far beyond the reach of the sun are exposed to deep-time irradiance from cosmic rays. Over millions of years, such exposure can create complex organic residues, polymer-like substances, that fragment in unusual ways when heated. These residues, similar to tholins found on Pluto and Titan, could sublimate unevenly, producing jets with different optical or physical properties than ordinary cometary dust. Yet even here the puzzle persisted. Organic sublimation can be erratic, but it is rarely disciplined. It does not produce million-kilometer linear jets with unwavering alignment. Next came the most cosmic framework of all dynamics shaped by galactic history. Some proposed that Atlas might be the relic of a catastrophic event in another star system, a fragment cast outward during the collapse of a super-Earth or the ejection of a planetary shell stripped by tidal forces. Such an origin could explain its mass and resilience. A fragment of planetary crust or mantle could survive interstellar transit intact and behave in unfamiliar ways when heated. If Atlas were composed of high-density mineral phases, crystalline lattices, silicates, or exotic metals, its response to solar heating might diverge from ordinary comet behavior. Jets could emerge from deep fissures unaltered by rotation due to internal rigidity. The uniform coma could be the result of reflective mineral dust rather than volatile sublimation. This interpretation elevated Atlas from a cometary oddity to a planetary artifact, not engineered, but born of a broken world. A shard of geology drifting for eons across the dark, now wandering into our solar system like a fossil carved by planetary catastrophe. Yet even this evocative hypothesis faltered at certain edges. A fragment of a planetary body should exhibit irregular brightness as it spins. Atlas did not. It glowed with the unwavering calm of an object whose surface properties were smooth, not jagged, as though polished by processes unrepresented in planetary geology. One of the more esoteric ideas invoked quantum field interactions, the possibility that Atlas had passed through regions of space shaped by exotic fields, perhaps even remnants of scalar phenomena or dark energy gradients. Some theorists speculated that prolonged exposure to such environments could restructure material at the molecular level, granting it unusual thermal, reflective, or dynamical properties. But such theories remained largely theoretical, with no clear way to tie the behavior of Atlas to the faint signatures of quantum cosmology. Other explanations drifted toward interstellar chemistry, the idea that complex organic or metallic compounds formed in the intense radiation fields near stellar nurseries might sublimate or fracture in unexpected patterns. Yet Webb's incomplete spectra offered no decisive confirmation. Still others turned to comet ancestry models. If Atlas had formed not in a stable planetary system but in a chaotic region, a young star cluster, a binary star gravitational resonance, or the outskirts of a supernova remnant, its properties might reflect the extraordinary pressures and temperatures of such birthplaces. Perhaps its uniform coma was a product of grains forged in intense magnetic turbulence. Perhaps its trajectory was a relic of long-lost gravitational dance with massive stellar companions. But even these exotic birth narratives face the same obstacle. None fully explain the collimated jets, the flat light curve, the reverse tail, the mass anomaly, and the trajectory alignment all at once. And so the broader scientific landscape began to accept a quiet truth: Atlas did not fit neatly within any known category. It also did not scream for extraordinary interpretation. It lived instead in a liminal space, a grey zone between categories where known physics could explain pieces of its behavior but never the whole. This zone was not a failure of science. It was a frontier a frontier where nature becomes strange, not because it is unnatural, but because humanity has only begun to map the vastness of interstellar phenomena. Atlas was a reminder that the galaxy is not composed solely of the familiar. It is stitched together by extreme places where chemistry, gravity, radiation, and time create objects that defy expectation. In this broader universe of explanation, Atlas's anomalies were not evidence of intent or design. They were evidence of possibility, a sign that the cosmos still holds material structures and histories unaccounted for in current theory. A sign that interstellar space may contain classes of objects, fragments of lost worlds, relics of violent formation shards sculpted by astrophysical extremes that humanity has never before encountered. Perhaps Atlas was one such relic. Perhaps it was many of them at once. Perhaps it belonged to a category not yet named. Regardless of origin, the object stood as a testament to the complexity of the universe, an emissary from a realm of physics just beyond the reach of present models, beckoning scientists to widen their frameworks and expand their imagination. For in the vast dark between stars, nature has had billions of years to experiment, and Atlas was one of its results. As 3I Atlas drifted inward along its improbable path, a quiet tension began to settle across the astronomy community, a tension shaped not by fear but by anticipation. For all the speculation, all the debate, all the anomalies that had stirred scientific imagination for months, the object itself had not yet reached the moment when its deepest secrets would be forced into the open. That moment lay ahead in mid-December when Atlas would make its closest approach to Earth. It was a milestone that existed not in narrative but in mathematics, a point in space and time where every telescope sensor and array humanity had built would converge upon a single silent traveller from the stars. In preparation for this, observatories across the world revised their schedules. Time, once reserved for galaxies, nebulae, and exoplanet atmospheres, was reallocated for Atlas. Researchers who once specialized in stellar evolution found themselves discussing comet dynamics. Particle physicists asked about dust grain scattering. Solar physicists studied tail reversals and jet morphology. This was the rare moment when a single object, faint, distant, and unresolved, commanded the attention of multiple disciplines at once. Astronomers understood that the December approach represented a window of unprecedented clarity. At its closest, Atlas would be bright enough for even moderate telescopes to dissect its coma, track its jets, and measure its rotation with unmatched precision. Larger telescopes, Keck VLT Subaru, had prepared coordinated observation intervals capable of capturing the nucleus, with resolutions far beyond what had been possible in earlier months. Space-based observatories unburdened by atmospheric distortion would join from above the clouds, Hubble poised for optical imaging, Webb ready to pry open the object's chemical secrets through deep infrared spectra. If the object held structural symmetry beneath its luminous haze, December might reveal it. If it possessed unusual chemistry, December might expose it. If its jets were indeed fixed and collimated, December might confirm it. If its rotation was slower, faster, or deceptive, December would force its truth into the light. The forecast among researchers was simple. The data flood would be extraordinary. For months, scientists had been working with incomplete information fragments of clarity surrounded by fog. December promised to dissolve that fog. With the sun no longer masking the object, with Earth's position perfectly aligned for prolonged visibility, and with the object close enough to magnify its anomalies, the observational capacity of humanity would reach its peak. The entire interplay between light, dust, and structure that had resisted interpretation might finally break open into knowable patterns. Yet as the date approached, a different kind of anticipation emerged, one quieter, more introspective. Among those who had studied interstellar objects for years, there was an awareness that such opportunities were fragile. Oumuamua had slipped away before science could isolate its form. Borisov fragmented before pristine data could be collected. Atlas, though behaving erratically, had so far remained intact, but no one knew what stresses it might face as it neared perihelion. A single fracture, a shift in rotation, a directional outburst, any of these could obscure the very features researchers hoped to observe. Thus December was not only an opportunity, it was a race. Within research institutions, teams prepared software pipelines to process incoming data in real time. Photometric campaigns were synchronized across continents so that rotation curves could be mapped continuously. Instruments capable of detecting non-gravitational acceleration were calibrated to unprecedented sensitivities. The hope was simple. If Atlas deviated from expected motions, the deviation would be caught. Instruments that normally required weeks to schedule were suddenly placed on rapid response standby. The Minor Planets Center issued bulletins urging early reporting of any faint detections. Even amateur observatories, small private domes scattered across backyards and hillsides, joined the global effort ready to contribute high-cadence imagery that, when stacked and cross-referenced, could reveal subtle changes invisible to any single observer. This was the spirit of modern astronomy, thousands of eyes focused upon one mystery. And as the scientific world prepared for the moment of closest proximity, a deeper question emerged. Not one of physics, but of meaning. What would it mean if Atlas turned out to be ordinary? A comet merely misinterpreted through gaps in data? What would it mean if it were extraordinary? A fragment of a shattered exoplanet? A relic bearing signatures unfamiliar to terrestrial chemistry? A technological artifact, or something beyond even those categories? Would the universe become larger or smaller in such a revelation? These were not questions for instrumentation or software. They were questions for humanity itself. Questions that had been asked since the first time ancient eyes traced the movement of stars across the night. As December neared, the solar system seemed to hold its breath. Atlas approached silently indifferent to the anticipation it stirred, carrying with it no intention, no message, no hint of what it would reveal when illuminated at last. There are moments in the relationship between humankind and the cosmos where the distance between knowledge and wonder narrows to a fragile seam. The December encounter with 3 Atlas was one of them, a seam stitched not by certainty but by hope, curiosity, and the quiet reverence with which humanity greets the unknown. And whatever Atlas truly was, its closest approach promised to be the moment when speculation gave way to revelation, however incomplete, however fleeting. The universe rarely grants second chances. As 3I Atlas continued its measured glide through the solar system, drawing ever nearer to the point at which no instrument could ignore it, a quieter transformation began to ripple through the scientific world, one not rooted in data or instrumentation but in reflection. The debates that had surrounded the object, the anomalies that had resisted interpretation, and the theoretical landscape stretched to accommodate it all converged into a singular realization: some mysteries do not exist to be solved swiftly. They arrive instead to reshape the way humanity perceives its place in the universe. For all the precision and rigor that science demands, there exists a deeper undercurrent in the study of the cosmos, an acknowledgement that the universe is at its core a mosaic of the unfamiliar. Interstellar objects are relics of other suns, fragments of worlds that formed beneath alien skies. Each one carries not only the physics of its origin, but the imprint of time itself. Radiation-scorched surfaces, crystalline lattices, scars from collisions, and the faint signature of light that has travelled across unimaginable distances. 3. Atlas, with its contradictions and its quiet defiance of categorization, embodied this truth more acutely than any visitor before it. Its mass forced scientists to reconsider what interstellar debris could be. Its trajectory suggested that randomness may not always govern the cosmos as cleanly as assumed. Its tail appearing and vanishing like a shifting breath reminded observers that natural processes often unfold in ways that surprise even seasoned experts. Its unwavering jet, stretching into the void with disciplined symmetry, challenged the very models designed to explain cometary behavior. And its luminous haze, so uniform, so resistant to resolution, became a metaphor for the limits of perception. No matter how advanced the instruments, how refined the techniques, some objects reserve their true form behind veils we are not yet equipped to pierce. But beyond the scientific intrigue lay something more intimate, a sense of perspective. Humanity, perched on a small world orbiting an ordinary star, spends its existence gazing outward, driven by a quiet longing to understand what lies beyond the borders of familiarity. Interstellar objects are rare visitors' messengers, neither sending nor seeking, but carrying with them the silent histories of places we cannot see. In Atlas's presence, that longing deepened. What if the universe is not quiet, but full of travellers' fragments, relics and signals that simply pass us by? What if the objects we label as comets or asteroids are not mere rocks, but chapters from stories written in other solar systems? What if intelligence too has left traces faint eroded by time, drifting invisibly across the galaxy? Such questions do not weaken science, they expand it. They open doors to humility, reminding humanity that certainty is a fragile construct, always subject to revision in the face of new evidence. Atlas did not need to be artificial, extraordinary, or impossible to provoke this transformation. Its power lay in its ambiguity, its refusal to sit neatly within the boxes prepared for it. The closer Atlas came, the more the astronomical community felt the weight of this moment. Not because the object posed any threat, but because it represented a turning point. Never before had an interstellar visitor been so massive, so puzzling, so layered in its behaviour. Never before had science been granted such an extended opportunity to study a messenger from beyond the sun. As the final days approached, those quiet nights when researchers across the world aligned their telescopes with patient anticipation, the world held its breath, waiting for whatever clarity or confusion would follow. Some hoped Atlas would reveal the ordinary, others prayed for the extraordinary, but all understood that the truth, whatever shape it took, would ripple through the foundations of astrophysics for years to come. For in the heart of this visitor wrapped in dust, jets and starlight lay a reminder older than any scientific theory. The universe is vast, the universe is ancient, and the universe is not yet finished teaching us how to see. And now, as the long arc of Atlas's passage softens into memory, the pace of this journey slows. The voices of instruments fade, the sharp edges of debate smooth themselves into gentler contours, and the object itself drifts once more into the quiet that has always held it. There is a moment when the lights of the observatories dim and the last images settle into archival stillness, when the universe seems to take one long, steady breath. It is in that breath that the meaning of this encounter unfolds. For all its anomalies and unanswered questions, Atlas was not a puzzle to be conquered, but a companion to wonder. Its presence encouraged the mind to stretch, the imagination to rise, and the heart to remember that mystery is not a barrier to understanding, but the path that leads toward it. Many things remain unknown, its true shape, its deep composition, the nature of its jets. But this unknowing is not a failure. It is an invitation. The stars have always given such invitations. They speak not in certainty, but in quiet pulses of possibility. And as Atlas continues its long voyage away from the sun, carrying its secrets into the vastness from which it came, humanity is left with something softer, something enduring the sense that we too are travellers, brief visitors in a universe filled with older stories. So let the object drift, let the questions linger, let the night sky remain a place where curiosity outweighs fear, where wonder outruns explanation, and where every new visitor reminds us how much beauty lies in the spaces we have yet to understand. The cosmos is wide, its silences are gentle, and its mysteries like Atlas move through the dark with a grace meant to calm rather than disturb. Sweet dreams,